So in 1924, Louis de Broglie proposed that particles could have wave-like character in addition to their particle character. And so electrons are particles, but they can also act as waves. And the wave nature is most clearly seen in electron diffraction. So this is very much like light diffraction. So the interference pattern here is not caused by pairs of electrons interfering with each other, but single electrons interfering with themselves. This is weird. So proof of that came in 1927. You take an electron source and shine electrons through this screen with two slits, and we see an interference pattern much like that we see with light. So electrons produce an interference pattern the same as light waves do. What's very strange about this is this interference pattern is coming from one electron interfering with itself. The wave nature of one electron going through the two slits interfering with itself just like light does. I know. What? That is weird. It's very weird. If electrons were particles, this is what we would expect to see. As the particles were coming through here, they go through the slit, they keep going until they hit the screen, and we'd see two bright lines. That's particle behavior. So the wave nature of the electron is an inherent property of the individual electrons. De Broglie predicted that wavelength of a particle was inversely proportional to its velocity. So an electron is not electromagnetic radiation. It does not travel at the speed of light. So this is known as the de Broglie relation. The wavelength of a particle is equal to Planck's constant divided by the mass times the velocity. That looks, unfortunately, like nu. That's an italic V. Yeah, sorry about that. That's V for velocity. And here's Planck's constant, the same Planck's constant we used before. So we can answer questions like this. What's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. So here's our de Broglie relation. Lambda equals h over mv. And we need Planck's constant. So we're going to be using lambda equals h over mv, where h equals 6.626 times 10 to the minus 34 joule seconds. We're given a length there, so that would be the wavelength, right? The wavelength is approximately the length of a chemical bond, so the wavelength is going to be 1.2 times 10 to the minus 10 meters. So we've got lambda, we've got h, we're trying to find v. What's m? The mass of an electron. Can't use one atomic mass unit. Well, it wouldn't be. It'd be approximately 0. We can't use that. Hey Siri, what's the mass of an electron?
The electron is a subatomic particle, symbol E or Greek letter beta, whose electric...
Oops, I interrupted her. What is the mass of an electron? What is the mass of an electron?
Here is what I found.
Yeah, that doesn't help. Good grief. Siri, you failed me. It gave it to me in atomic mass units. Here we go. 9.109383561 times 10 to the minus 31 kilograms. We'll go with 9.109. Okay, so the mass, 9.109 times 10 to the minus 31 kilograms. Okay, we got a mass. I don't expect you to know that number. I don't know that number. We look it up if we need it. We don't use it much at all. Okay, so we want V. So students sometimes rearrange this equation badly. Okay? We've got a fraction here, so the best thing to do if you struggle with algebra is to cross multiply, get rid of all the fractions. So cross multiplying, I'm going to get sorry, that's not H, that's a lambda. Lambda times mv is equal to H. I'm multiplying the top of this side and the bottom of that side, the bottom of this side, which is a 1, and the top of that side. And then I'm going to divide to isolate the variable of interest. So I'm going to divide by lambda and m. So the lambdas cancel out and the m's cancel out. Common mistake when rearranging this equation is to inadvertently solve for 1 over v, and then, get the wrong answer. Okay, so our velocity is Planck's constant divided by lambda times the mass. So we've got all these weird units here. Let's just plug them in and see what happens. So we can always erase things and fix it later. So 6.6 times 10 to the minus 34 joule seconds, divided by the wavelength, 1.2 times 10 to the minus 10 meters, and the mass of an electron, 9.109 times 10 to the minus 31 kilograms. I would not try to trick you with the units of this on an exam. A joule is equal to a Newton meter, which is equal to a meter per second squared, kilogram. Start that over again. A Newton we're going to end up with kilogram meter squared per second squared. Yeah. So kilograms and meters and seconds are the units that we want. And so we've got meters and we've got kilograms and we've got seconds. And if you're interested, I'll show you later. This is going to work out to have units of meters per second. So we can just do the math on the calculator. 6.626 times 10 to the minus 34. What do you think? Is the speed of an electron going to be a small number or a big number? I hear small and I hear big. So my calculator is showing me 6061770.41 meters per second. So for two significant figures, that would be 61 meters per second, right? No. You awake? Be careful when you round. 6.1 times 10 to the 1, 2, 3, 4, 5, 6. 6 million meters per second. Very different than 61. And if you don't see the difference between 6 million and 61, I'll have some financial transactions with you and make a bundle off of you. So there's the velocity of an electron. Large things tend to move slowly and small things tend to move quickly. An electron being very, very small moves very, very fast. Now, is it as fast as the speed of light? No. Nothing but light moves as fast as the speed of light. Things get very weird when other things approach that speed. So, the uncertainty principle. When you try to observe the wave nature of the electron, you cannot observe its particle nature. This is that juxtaposition or superposition, that's the word, superposition of two states. The electron is acting as a wave and a particle, but when we observe it, we force it to act as one or the other. We observe the wave nature as the interference pattern, and we observe its particle nature as its position, which slit it is passing through. I'm feeling, oh, here it is. So this is I'll get back to the rest of that slide. This is very, very interesting. So you can take that electron diffraction setup, where you see the diffraction pattern, and if you shine a laser beam through that, the laser beam allows us to detect which slit an electron is going through. In essence, we're observing the electron. When we do that, we get two bright lines instead of the interference pattern. Take away the laser, interference pattern comes back. It's freaky. You can't observe both of them at the same time. You can observe one or the other, but not both. So the wave and particle nature of the electron are complementary properties. The more you know about one, the less you know about the other. And this is the basis of Heisenberg's uncertainty principle. So the more accurately you know the position of the electron, the less you know about its speed, vice versa. So I'm not going to test you with this, but there may be a homework problem that makes you use this equation. How does this work? So delta x is the uncertainty in the electron's position. So x is the position, delta x is the uncertainty. The uncertainty in the position times the mass times the uncertainty in the velocity. That has to be greater than or equal to Planck's constant divided by 4 pi. Aren't you glad we don't have to derive that one? What this means is we cannot simultaneously measure the position and the velocity of an electron. We can do that with real, regular objects like a baseball. You can say exactly where it is and how fast it's traveling. You can do that with a spaceship. But you can't do it with these absolutely small particles because they obey different rules. According to classical physics, particles move in a path that's determined by their velocity and their position and the forces acting on them. We understand this, even if we've never had physics, just from our experiences with real-life objects. Small children do experiments with this all the time. They throw things and see what happens. They drop stuff off the high chair. They're studying physics. So this is called determinacy, that the present determines what the future's going to happen, or what's going to happen in the future. So we can't know the position and the velocity of an electron at the same time. We cannot predict the path it will follow. So this is known as indeterminacy. We can only describe the future in a statistical way. We cannot say this particle is going to do this or that. We can say, on average, this might happen, or 90% chance that this thing's going to occur. So the best thing we can do is describe the probability that an electron is found in a particular region using statistical functions. So essentially a probability distribution map. Can't say exactly what's going to happen. Any questions about that? So here's a picture of something familiar. This is the classical concept of trajectory. So here we have a baseball player hitting the ball, and it goes up because he hit it with force. It's experiencing wind resistance and a pull of gravity downward, and so the ball takes this very predictable trajectory, And the baseball player, without knowing any physics at all, his mind understands and can predict where that ball's going to land, and he gets under it and he catches it. That's determinacy. The present determines the future. Electrons don't act like that. So here we have another baseball thing here. Pitcher pitching a ball. If the pitcher throws the ball exactly the same way every time, the ball is going to go to exactly the same place, right? A pitching machine can do that, just bang, 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 same place every time. If you do that with an electron, it does not go to the same place every time. That's about all you can know, is that it will not go to the same place. That's disturbing. It should be disturbing. So if we were pitching electrons, these little white dots represent electrons being pitched at the catcher here. We can draw some circles and say that there's a can't see that, 40% chance that the electron will hit within this circle, a 20% chance within this circle, a 70% chance within this larger circle. So we can draw these regions and say there's a probability that it will go there. But there's also a probability that it's going to come up here and hit this lady between the eyes. Could happen, right? Very unpredictable. So we can look at we can make a graph here, number of pitches against distance from the center of the strike zone. And so we can see that the highest probability that most of them are going to be closer to the strike zone, the center, and as we move away from the strike zone, the number of pitches that go there is going to diminish. That makes sense? It's sort of like a bad pitcher, except this electron pitcher is pitching them exactly the same way. It's just that electrons do not behave in a determinate way.